Thank you very much. Thank you for the invitation. This looks like an exciting workshop with a remarkable group of people that I want to talk to. And so I was asked to give a review about how we can approach quantum gravity from a Bootstrap perspective, with an emphasis on symmetries. And unfortunately, I have very little of substantial things to say about symmetries. Nothing really has been done yet in that context, especially the notorious question, which is really the question.
Is there a microphone?
There is supposed to be a microphone, but it works. I can speak louder. Is that okay? So maybe now it is working. You don't hear anything on the back?
Here, but I think it would be better.
Usually maybe the acoustics are not great, because usually there's no problem in hearing me. Anyway, so the question of the workshop is about the symmetries in quantum gravity, absence of global symmetries in quantum gravity. How can we quantify their failure? And this is something that we should be able to approach from an abstract Bootstrap perspective, but essentially nothing has been done. So what I will do is spend most of my time giving you an overview, conceptual, as well as a few hints of the... Can you hear me now? A few hints of... Also, there's a lot of seats in the front. But you guys should be hiding in the back. I used to do that in high school when I was doing the homework for the next hour. But anyway, so I will give an overview, both conceptual and with some presentation of some more technical results, and please ask questions. And then at the end, I have some musing comments about symmetries, but it will be very much open-ended, and time permitting, we'll move to the blackboard and perhaps open it to the floor. So the starting point is what I would say is our working hypothesis or conservative assumption that the recompletion of gravity should obey all the standard rules of quantum mechanics, as well in causality. Quantum mechanics is I think, is uncontroversial. Causality needs proper definition. And again, the most conservative approach is to retreat to observables, which, according to whether we are working in asymptotic flat space or asymptotic ADS space, would be the S matrix or conformal field theory correlators, and enforce general principles which should be properly axiomatized. There's some issue with the mic. Can you? Is it better now? I have nothing to say about the sitter, but it's sort of clear what to do. It's extremely clear what to do in the sitter space. We have to use the usual conformal bootstrap, including the stress tensor, which is dual to bulk gravity. Also clear, although somewhat more tentative, what to do in asymptotic flat space. We do the standard arithmetic bootstrap, but now we enforce the presence of a master spin 2 particle. And so, at least superficially, from this naive conservative viewpoint, inclusion of gravity seems straightforward. Just include stress tensor or spin 2 particle. So let's start with ADS, where I think the axiomatic framework is completely uncontroversial. By definition, quantum gravity in asymptotic LDS is just equivalent to conformal field theory on the boundary. And the axiomatic viewpoint that I will use, and I will only use this axiomatic viewpoint, is the standard Euclidean CFT axioms, which we are all familiar with. The CFT is abstractly defined in terms of a set of local operators, which equivalently states, because we have a completely rigorous state operator map, the OP is convergent We have a notion of unitarity, which can be made very precise and involves certain unitarity bounds in conformal dimensions, as well as positivity of squared P coefficients. And although my focus will be on local operators, it's also clear how one can include conformal defects if need be. So again, this is something I will come back in the discussion. This is the standard axiomatic framework of conformal field theory, and it's very much within the Osterwalder-Schroeder-Whiteman framework. So it's not about algebraic quantum field theory. Algebraic quantum field theory is mysterious. I think you may sneak in there some extra assumptions that I would like to avoid, so I want to stick to this super conservative viewpoint. This is something we know, and this is something we're going to try to leverage as much as we can.
I'm just curious, Leonardo, do you really think, for example, there's a complete uncontroversial set of axioms for QFT at the level? For example, Whiteman is not complete, right? It leaves out the stress tensor and so on.
No. When I say Whiteman, I say in Whiteman's spirit. So I can really give you a complete list of conformal field theory axioms, which have the ones that have been used, for example, the conformal Bootstrap, and we may discuss whether it's complete, but it's true. It's a list of things that are true.
In 2D, I'm sympathetic to that.
Even in higher D. Let's postpone the discussion to the end.
It's not better than the algebraic, but okay, fine.
Well, I don't know if it's better, but can we postpone this discussion?
Sure.
Yes.
So one of the issues with Whiteman is that Whiteman is true on a subplane, right? And it doesn't guarantee the conservation of the stress tensor.
So there are some references here, and we can get into the discussion perhaps at the end. The most conservative viewpoint, you start with Euclidean conformal field theory in RD, and there I think there is a very well-defined set of axioms that we can hopefully all agree on. Then there are somewhat subtle reconstruction theorems to go from Euclidean to Lorentzian, and let me highlight this very nice paper.
The more subtle things have to do with modular invariance and so on.
Yeah. So I'll get to that. So in the original papers on the reconstruction theorem, Osterwalder and Schroeder made a very mysterious technical assumption about the growth condition on endpoint functions, which is very delicate because even to analytically tune a single 4-point function of local operators in Euclidean space to Lorentzian, you need to assume something about all endpoint functions of local operators. So that's very subtle, and in this nice series of papers, these authors were able to prove the standard, the analytic continuation Lorentzian space purely for the point functions without any assumption about growth condition of endpoint operators. So I would say we have made progress, and at least at the level of endpoint correlation function local operators, I think we have a perfectly well-defined set of axioms in RD, as Danny was already mentioning. Of course, other topologies may be important, and we can discuss that. But at least let's start with this, which is a basic set of, I would say, clear desiderata. And then, of course, since we're trying to do quantum gravity in ADS, the basic observer is a Poisson function of the energy tensor, which is technically complicated, but thanks to work by our wonderful colleagues, this has been done in full glory in the 4-dimensional case. Okay, so flat space is a bit harder, and in dimension greater than 4, nevertheless, the working hypothesis is that quantum gravity has a unitary in causal S matrix with a Regge behavior strictly better than 2, which is the Frossard bound. Now, my conventions, I apologize about this, but S is a standard magnitude variable, which is the center of mass squared, and what people would usually call T, I'm calling U. That's momentum transfer. And theta is the scattering angle for 2-to-2 scattering. And the assumption here, I'm writing here precisely, is that for fixed momentum transfer in large energy, you need to divide by s squared to get 0. So that means, the number of powers of s in the denominator are denoted as subtractions. So that means that m over s squared decays at infinity. So that means that you can take a contour integral, you can neglect the contribution at infinity, and then you can start writing down dispersion relations. So the parlance here is that twice subtracted dispersion relations are valid. I will get to the point about smearing a little bit later, but I would say that thanks especially to the work of Herring and Zhiboyedov, although this is not proven from the axioms, and I remind you that proving the validity of dispersion relation is extremely complicated, even in the vanilla case of get quantum field theory, where we think they're valid, but deriving them from the axioms is very hard. And so here, of course, we're a little bit more on tentative ground. These are going to be our assumptions. So you could take them as part of the axioms, or perhaps hopefully one day derive them in a fuller story from some more primitive set of axioms. Of course, ideally, we would like to derive these requirements by carefully taking the flattest mean from ADS, and I will come back to that at the end. I think we're getting close, but we're not quite there fully rigorously. Yes.
So the rigid behavior is supposed, so here is at the level of an extra assumption, but at the end of the day, do we expect to get it from causality?
Absolutely. So absolutely. So the way this works in quantum field theory, it can be derived from causality, essentially, from unitarity and causality. And I will later on sketch the argument that Herring and Zhiboyedov gave in the context of quantum gravity, which again uses some notion of locality, which is encoded in the fact that the amplitude should behave sub-exponentially, which is a reasonable requirement. Again, nothing is proved. I mean, this is a set of axiomatic requirements for the S matrix, which hopefully will one day derive from taking the limit of ADS. Now, you may notice, of course, here that I'm restricting to dimension greater than 4, because in 4 dimensions there are notorious infrared issues, such that the S matrix of graviton is not even well defined. You need to consider either some more inclusive observables, various proposal for, in the spirit of Faddeev Kulish, appear to fail. There's a nice series of papers by Wald and collaborators on this. I will really have nothing to say about 4 dimensions, except for by pointing out that, of course, ADS4 is a wonderful IR regulator. So if we really think we can take the limit rigorously, by doing that, this will define for us a set of jets in flat space that arise by taking the large radius limit of ADS. The jets will come with a certain size, which is essentially the ADS radius, which acts as a regulator. And I think this is an excellent research problem to define exactly what these jets are by taking the first limit of ADS4.
So does d bigger than 4 mean d equals 5 and 6?
The involvement is 5, 6, 7, 8, up to. So,
You're assuming an ultra. What are you assuming?
string theory, for example. We're doing quantum gravity, right? So this is.
Is d bigger, d less than 12?
Maybe, yes. Well, so that's part of the question. Can one prove from the axioms that D has to be smaller than 12? That would be wonderful. But we're not going to assume any microscopic description at this stage.
I'm going to comment more on these jets that you need to get from the ADS4 limit.
No, I'm suggesting this is a research problem. I haven't done anything about it, but it seems like a natural idea. So, okay, so we're going to organize our thoughts using effective field theory. And so this is, of course, Einstein Hilbert, possibly supplemented by a negative cosmological constant, and of course an infinite set of our derivative corrections. And if so wish, we could also include additional light degrees of freedom with spin smaller or equal than 2. For us, they will count as matter. Okay, that's perhaps slightly unconventional, but we will see that there is a very sharp conceptual point that separates massive degrees of freedom of spin 2 with massively closed space on spins higher than 2. So the scales in the problem are the cutoff n, which is where the new physics enters, where the effective field theory stops being valid, and of course the Planck scale. And loop correction and effective field theory are controlled by these ratios, m over n Planck. So if, so long as we have a hierarchy of scales between the cutoff and the Planck mass, then the effective field theory can be slightly perturbative. In fact, to the approximation, we can just do 3-level. Of course, if the new physics arises strictly at the Planck mass, then we are in a fully non-perturbative regime, and we cannot really trust the classical or classical level approximation of the effective field theory. And here, the crucial physical expectation, which comes from a beautiful thought experiment by Camagna, Alessandro Dazzini, and Ciboiedo, by Brigetti Scams, is that the cutoff is not any scale, but is precisely should be identified with the mass of the lightest higher spin state, where higher spin means spin greater than 2. And once you made the identification, you further predict from Wilsonian intuition that the higher derivative coefficient should be of order 1. Okay, so that's, I invite you to read the paper if you haven't yet. And one of the goals of this research program is to make this precise. And I would say we have succeeded. And that will come in later slides.
So in QCD, there are states with spin greater than 2. What are we supposed? So does that mean the cutoff is at the QCD
Absolutely,
scale?
yes, absolutely.
So why haven't we seen? I mean, maybe we could have seen. Is it ruled out r to the 4th over the QCD?
Well, I mean, sorry, this is gravity, so I don't know what you're talking about. You're talking about pions, maybe.
Well, I mean QCD coupled to gravity.
Well, I don't know. QCD coupled to gravity is
So this
the Planck
predicts-
scale. The Planck scale is immensely higher. I don't know when we do.
Wouldn't this argument say the cutoff should be at the QCD scale?
But the cutoff is at the QCD scale, that even without gravity, right? If I look at the chiral Lagrangian, obviously that is trustworthy only, and low energy is much more than the QCD scale. I don't need to invoke gravity for that.
I mean, but I just take QCD with quarks and gluons. It's still true that there's a state.
You're just saying that there's a loop correction in QCD that gives an R-squared term like that.
Yeah, there is also loop correction to given an term, but I'm not sure I'm quite seeing your point.
I think that's the answer to Daniel's question.
Yeah, there is also loop corrections of that order, and that's fine. But I don't want to talk about quarks and gluons, right? So I'm a bootstrapper. All that matters for me are asymptotic observables. So you have to phrase your everything has to be phrased in terms either of gauge invariant local operators, in terms of asymptotic gauge invariant states. And then yes, of course, there are glue bolts or mesons of spin greater than 2, and that's all fine. Then they are indeed at the QCD scale. Yes.
Just one other thing about Daniel's question. In fact, in the standard model, right, if you integrate out all the massive fields, the first correction to the gravity EFT is it was like Riemann cubic. It was like one of the neutrino mass square, and we can't even see that yet.
Yeah.
So.
No,
these-
I mean,
these
I think
things are there, but,
the
you
question
know,
was a
we can't
conceptual
detect
one,
them.
obviously not
Yeah.
in terms of measuring these effects in the lab. Anyway, so keep this in mind, these 2 points, m over n Planck controls loop corrections, and the cutoff is really the higher spin scale. So let me now quickly go through the kind of physical regimes, starting with flat space. There are only 2 scales, m and n Planck. And of course, if m is lower than n Planck, we are in the situation where we can treat the theory is effectively classical. And we have a prototype for this, which is just 3-level string theory, or perturbative string theory, where the higher spin states are at the string scale, which for small coupling is parametrically smaller than the Planck scale.
Leonardo, quick question. Instead of the string scale, could you have like a Kaluza-Klein scale?
Kaluza-Klein wouldn't do, because Kaluza-Klein is spin 2 or lower.
But the effective field theory certainly changes when you get to the Gecke scale, no?
The effective field theory changed, but what is important for the Kemp's argument are states which are spin greater than 2. That's one essential point. So, and so here we have a sub-problem, which is a symmetric in its own right. So of course, in Taylor string theory, we have this wonderful set of meromorphic amplitudes, which are generalized via Zora-Shapiro, and in fact, you can consider arbitrary 2-to-2 scattering of the massive string states or endpoint scattering or what have you. And here you must have then a consistent set of meromorphic S matrices with factorization, have positive residues. From a space-time perspective, this looks like a complete miracle, which is only clearly understood from the worksheet derivation of these amplitudes. And so there is here a pretty reasonable hypothesis that perhaps string theory is the only consistent framework to get tree-level extensions with higher spin states of Einstein gravity that obey all these consistency conditions. And we would like to carve out the space of possibilities and perhaps prove this hypothesis. And here we have a very precise tool that I will review later on, which is, as I was already mentioning, dispersion relations. And the tool is rigorous in the sense that it's what's called the dual bootstrap. So we carve out the space of possibility. Any stage of our progress, we have rigorously excluded some theories, and if the process converges, then we have a bunch of possibilities left. We don't know whether they're realized or not, but whatever is excluded once is excluded forever.
So
Now-
does your hypothesis exclude Vasiliev then?
Vasiliev theory is in ADS, right? So here we're flat space at this stage.
Vasiliev's theory is flat space too.
To the rest of my knowledge, nobody has made it fully precise.
I mean, I think QCD is another example. So you would say QCD is an example of string theory according to this hypothesis, right?
We're doing quantum gravity.
But QCD can exist in a gravity theory, right?
Yeah,
So-
you can have QCD plus gravity, I hope.
Yes, but tree
You say it's
level.
a string theory, I mean, there is
Tree
a
level.
QCD string.
The cutoff is much smaller than the Planck scale.
What does tree level mean?
For what?
I mean, I have a set of words here. Please read them. Meromorphic S matrices. Meromorphic S matrices.
Okay.
Okay. So we're looking at a set of meromorphic S matrices like the string tree amplitudes that contain higher spin states. QCD is not like that, and that's the problem that we are trying to discuss.
Maybe large N QCD.
Large N QCD is extremely interesting, and I'm working on it, and pretty much has a very similar flavor, except of course there's a crucial distinction: you don't have a master spin 2 particle. The presence of a master spin 2 is supposed to be extremely constraining, right? So indeed, in this program, we should contrast the rigidity of matrices that have a master spin 2 with the enormous flexibility of ones that don't have it, because any large N gauge theory is supposed to give you a set of such amplitudes. Now, if N is order n Planck, we are in the regime of quantum gravity, and here it's harder. I will say very little about this. There's beautiful work by a set of authors, Vieira, Penedones, Guerrieri. Here, the main tool is you make an ansatz, sufficiently general ansatz for how an fully non-perturbative amplitude should look like. Of course, this is much harder because the amplitude is the analyticity properties are very unclear. You can have all sorts of extremely complicated cut structure. And then you populate the space of amplitudes within these answers by imposing consistency condition. And the idea is that if your answer is general enough, now you're working from the inside out. You populate things, the things that you find are consistent within the space of axioms that you have assumed. And what is outside, well, we don't quite know, but presumably is inconsistent because we haven't reached it. But the story here is a little bit less systematic than the consistent carving out from the outside. Nevertheless, what's remarkable is that when both approaches are available, they appear to agree, to give you the same exclusion boundaries, which means that this is actually also very likely the truth. Okay, so in ADS, we face, of course, a complication. We have an additional scale, which is the ADS scale, and so the story is a bit more elaborate. So I'm identifying here 4 regimes. One is when you have a two hierarchies. The cutoff is much greater than the DS scale, and which is much smaller than the Planck scale. And this is the regime where Einstein gravity, in fact, weakly coupled Einstein gravity should be reliable. And so there is a famous conjecture by HPPS that any large N CFT, large N means that you can neglect loops in the effective field theory with higher spin gap delta higher spin, which means that the N here is much more than one RDS. If you are in this regime, then the theory is holographic in this sense, in this technical sense that the dual description in terms of tree-level Einstein gravity is reliable.
What aspect of this is conjectural?
I would say there is by now a proof.
Yeah, that's what I thought.
Well, but that's what's coming.
I see.
And the proof will again use a version of dispersion relation, which will be in the context of conformal field theory. Now, you don't have to assume this for both hierarchies. You could assume that the cutoff could be of order of RADS or perhaps a little bigger. And a prototype for this is tree-level string theory in ADS. For example, our favorite example, ADS phi times S phi, which is due to large N equal 4 to pi Mills. But now, given that we don't assume a hierarchy between the higher spin cutoff and RADS, we're in the framework of finite stuff coupling. And again, there's been beautiful work by this, which I will only very briefly mention at the end, where again, this conformal theory dispersion relation supplemented by additional spectral data that comes from integrability, for example, are very powerful. Then let me move to this other regime, which is the regime where we're agnostic about whether the cutoff is, it could be all the way to the Planck scale or nearby, but we are assuming that there's a large separational scale between both the cutoff and the Planck and the ADS scale. And these are these mythical animals, the scale separated ADS vacuum. Hopefully we'll have a discussion about this at some point. I know people here are experts, and of course it would be, analyzing this from the point of view of the string theory landscape with precise construction is extremely hard. People fight and get into all sorts of bitter arguments. And so it would be wonderful to be able to address the question from this very conservative axiomatic viewpoint. Yes?
You don't have the KK scale in here, so how can you say that's scale separated?
Yes, okay. Okay. You must be a mathematician. I need to consider the ADS in the appropriate number of dimensions. Let me put it this way. So in the case of
No, but M is your string scale, right? And scale separation, I would say separation.
Okay, you're right. Here I'm being a little imprecise. Yeah. I would say that in order to say that we have scale separated ADS vacuum, I need to make further assumptions that what are in this line. But these are necessary assumptions. But I need to say more to tell you that I'm scale separated.
Do you include ADS7 cross S4 in that?
No, ADS7 cross S4.
That was the question.
Yeah, that's the question, and he's right. I need to say more. And then finally, of course, if all the scales are the same order, then basically we have nothing to say. This is a generic CFT, and perhaps we shouldn't even talk about it because there's no obvious notion of emergent space-time. And then here we are back to standard numerical conformal Bootstrap. That's all we have. Okay, so sorry, this introduction took a little longer than I expected. I cannot possibly cover everything. I'll just give you a flavor of the very different things that have been done. So I will I will start with the symmetrics bootstrap, even if it's less clear-cut axiomatically, but technically it's much easier. And so then I will motivate the assumption that we're making about these scattering amplitudes a little more. And then see how we can use the technology of dispersion relation to derive rigorous bounds on effective field theory in the regime where the cutoff in fact the higher spin scale is much smaller than the Planck scale, and this will actually lead to a proof of the Kemp's scenario. And I will also make some brief comments about the black hole with gravity conjecture. And then I will switch to this problem that I described earlier, carving out the space of meromorphic S matrices that contain gravity. And then finally, I will talk about the ADS-FT bootstrap. These PERT-CFT sum rules are somewhat technical. We'll try to give you a flavor of how they are derived, and then this will lead to essentially a proof. We can discuss a fine print of the HPP's conjecture, etc. And then I will end with some very preliminary musings about gravity and symmetries, and open the discussion. Okay, so we're looking at the tutu scattering amplitude, and we're assuming so certain things are uncontroversial. It has a partial wave expansion on the physical S-channel cut. This is a statement about unitarity that is really quite uncontroversial. Ionicity across the cut and crossing symmetry. I would say if you don't believe this, then we can go home. These are basic assumptions. A little bit more tentative, but we will certainly assume it, is a standing ionicity, which there may be a blob here where complicated things happen, but far away in the complex S plane. Again, this is done at fixed U. The amplitude is analytic. And here is the one that is perhaps the most questionable and the most adventurous, which is the statement that Regge boundedness with spin strictly greater than 2 should obey along any ray, and this is the slogan that 2 subtractions suffice. Yes?
You said something earlier on the slide about meromorphic, but there's going to be a branch cut, right?
So this is, I'm now doing the general discussion. I will specialize to meromorphic live.
When you say analytic, it's analytic away from the cuts, so we're not taking into account multi-valueness?
Away from the cuts, yes. Okay, so for the perturbative, so there is an argument which I find convincing by, but again, everything is up for discussion, that this J smaller than 2 Regge behavior must really be true in quantum gravity. And notice that this is strictly better, a little bit better, than the so-called classical Regge growth conjecture of the TIFR people. And the physical root of the argument is really the statement that has been known for a long time, that no matter how large the center of mass energy is, if you fix the center of mass energy and you take input parameter to be much bigger than this combination, which is something you can always do in bigger than 4, then gravity is weakly coupled. And this follows in rather elementary way from the fact that the U-channel pole controls the behavior in this regime. And so you fix the energy, you fix S, but for B large enough, which is the same thing as saying that U or the momentum transfer is small enough, the scattering of gravity is just controlled by the U-channel pole. So this is a simple physical point that was emphasized already in the 80s by Matti Sciaffaroni and Veneziano. And so that means you know how gravity behaves in this regime, because you can just use classical GR. And then Herring and Zhiboyedov argued that allows you to control the behavior of the amplitude on the real axis, on the real S-axis. And the most conservative estimate works in dimension greater than 7, but if you're willing to be a little bit more adventurous and assume not just this leading pole behavior, but that the phase shift really equanalyzes, you can extend this to dimension greater than 5, and with somewhat additional assumptions about the behavior of gravity, which I think are still very reasonable, all the way down to equal to 5. And then once you have these estimates on the real axis, by assuming sub-exponential growth, you can extend this along any ray in the complex S-plane. Now, the same authors also argue that smear amplitudes, I will come back to the smearing procedure later, are in fact completely safe. You don't need to assume these are more adventurous models for how the phase shift behaves. The Born approximation, which is uncontroversial, is the statement that the U-channel pole dominates for large input parameter, is sufficient to give you the Rastelli behavior in dimension greater or equal than 5. Okay, so I would say we are on safe grounds. And then the idea is, which is an old idea, which has been, of course, used extensively throughout the history of post-World War II physics, and we are rediscovering old things. Well, we take this contour, we divide by sufficient number of powers of S so that we can neglect the contribution at infinity, and so we get something which is equal to 0. Again, this is done for fixed U with a contour in the S-plane. And this particular combination is cleverly chosen so that the ST crossing symmetry is respected. And then, well, you see this contribution, there are only two contributions here, one from the integral along the cuts, above the cutoff, and the other one is the integral in the red region here. One should be understood as what happens in the UV, the other is what happens in the IR, and so the fact that this is 0 tells you that you can rewrite the IR effective field theory coefficients in terms of certain sum rules that involve the UV spectral density. And you don't know much about the UV spectral density, you want to be agnostic about it, but you certainly know that it's positive from unitarity. Now, this is true in general, but it becomes really powerful, and you can do an extra calculation when in this regime where the effective field theory can be treated at 3 level. And then you get a rigorous set of sum rules that relate the 3-level effective field theory coefficient, the one that I was writing earlier, such as these higher derivative corrections to gravity in terms of precise UV spectral densities. And then notice that ST crossing is magnetic, but SU crossing has been broken by the fact that I decided to fix U and do a contour integration over S, which means that I should really impose it separately. And if I do, I find that the spectral density actually obeys additional constraints that must be there to compatibility with low energy SU cross.
And you drop the contour on the half circle because of the Reggie assumption?
Yes, yes. So this technology, so let's first illustrate in the case without gravity, where it's particularly simple. So suppose we are looking at 2-2 scattering of massless scalars at 3 level, and where I could include some additional self-coupling, but in fact it won't be important because it will be washed out by the subtractions. So I write down the most general analytic expansion of low energies, which has to be crossing symmetric, and it's G2, G3, G4 are my Wilson coefficients. And remarkably, the fact that these G2, G3, G4 obey some rules in terms of some positive spectral density, and additional there are these null constraints, means that not anything goes. You can actually derive rigorous inequalities, which are two-sided using semi-definite programming, and everything is homogeneous, so rescaling the coupling does nothing. So the best you can do is put bounds on homogeneous ratios like Gn over G2. Furthermore, by dimensional analysis, you have to include some powers of the cutoff. And so this leads to compact regions. I want to emphasize the word compact here, for these homogeneous ratios in units of the cutoff. So this is, I think, a remarkable conclusion that makes Wilsonian power counting fully rigorous. You could have suspected that the order 1 coefficients in the Wilsonian effective action were in fact not order 1, but order 1,000,000, or an order 10 to the minus 5, but no, they are truly of order 1 if you look at the scale of the plot. Anything that violates the order 1 coefficient by factor of 10 is rigorously excluded. By what? By UV consistency, the statement that the theory has to make sense in a far UV.
Yeah, I'm lost. If I divide by S squared, why does this go to 0 as S goes to infinity?
No. So this is, well, that's the whole point. The full amplitude decays at large S,
yeah.
But when I spin the low energies, each term violates the behavior more and more. And it's precisely the hidden.
This is
the
a
hidden.
low energy expansion?
This is a low energy expansion.
Is it asymptotic?
Oh yes, it's certainly. I mean, sure. It's just well, I don't know what if there are rigorous statements to that, but I don't care because I'm going to, when I divide by sufficient powers of S so that the amplitude is well behaved at infinity, what this coupling gives me is poles that I pick up at the origin. And those poles have to be equal to the integral over the high energy cut.
So this is the expansion at small s is at fixed u.
No, this is the expansion where everything is small. It's just the effective field theory expansion. Yes.
There are no logs to all orders in perturbation theory, no logarithms to all
No,
orders.
so this is where we're, the regime where we're assuming where we can treat the effective field theory strictly at tree level. So it's an excellent question how to systematically include loop corrections.
So it doesn't include loops.
No, you could of course start including loops, and there's work in that direction, but and it gets a bit technical, and I think there's still some unresolved issues. I will not say anything about that. Okay, so now let's go back to the problem of interest, which is with gravity, and here we face the issue, which is, I don't know why you want to think of it as a technical issue or a conceptual issue, that now we have a 1 over u pole, and so the kind of sum rules I was deriving earlier were derived by this naive Taylor expansion on u equal to 0. That cannot be done anymore. And actually there is a resolution which you work a little bit harder, and you find some improved sum rule where that truncates. You only have a finite number of terms in the expansion in U, which is given by this rigorous sum rule where you sum over the the UV spectral density. And then to make sense of this, you need to convolve with a suitable test function to derive bounds. And that's the smearing I was talking about. In fact, it turns out the smear amplitudes are completely safe even in gravity, according to the argument of Herring and Zhiboyedov. And the Fourier transform of U is the impact parameter, and the kind of test function we are convoluting by. So we have to find a test function such that the there's this usual semi-definite bound problem you have to keep in mind. You have to find a suitable test function such that the various Legendre polynomials that you're convolving the F with are positive. And if you find that, then you have a positivity rule that you can use to derive an inequality. And then you find the best F, and the best F looks like something like this. So you see it's localized in a region smaller than one of the inverse parameter scale. And this is very much a kinematic regime used in the camps of Spain, but now this allows to derive precise bounds. And so here is the highlight of this paper by Caroniot et al. Again, we are working in dimension greater than 4, and this is beautiful but extreme technical work because now you're looking at 2-2 scattering, which is of gravitons in any dimension. There is a gazillion tensor structure. Truly hard work. But when the dust settles, you find that these higher derivative corrections, which I'm parameterizing here in terms of certain powers of C, which is, I believe, the Weil tensor, really must obey rigorous bounds where in units of the higher spin scale, they are of order 1. And that, I would say, is a rigorous proof of the Kemp's conjecture. Okay. With rigorous bounds.
Leonardo,
Yes.
based on this, you would say that all these theories of gravity that people propose, where higher derivative terms are comparable to tree level, they're all in the swap. No?
Okay, so we have to be a little careful. So, for example, f of r gravity, where r is the scalar r, is not excluded by these bounds because it's f of r gravity can be obtained by coupling gravity to a scalar with a certain potential, integrating out the scalar, and that would not be excluded by these bounds. These bounds really probe this higher spin cutoff scale. So f of r gravity. So another way of saying this is that by using equations of motion, you can always get rid of the scalar r and of the Ricci r mu, and restrict yourself to correction that only involve the Riemann tensor.
I mean things more like Einsteinian cubic gravity and that kind of thing.
Yeah, but I mean, did you have any doubts that those were junk? So,
Why this choice of dimensions?
Yeah.
What happens at d equals 27? Could it shrink to a point?
oh well,
It looks like it shrinks as the dimension increases.
maybe it shrinks to a point.
Pardon?
Maybe it shrinks to a point. I don't know. We should ask the authors of this paper.
It's extremely difficult to implement the numerics, so that we only choose 3 particular dimensions that we feel a little bit easier and interesting to do.
So what about d equals 27? That's interesting.
Yeah, but it's extremely hard to implement numerics.
I think it would be a little bit too good to be true if you found the dimension come from string theory just from this kind of argument. This kind of argument. I think what I like about this research program is that how conservative it is. You're assuming almost nothing. And from almost nothing, you're getting a lot of mileage, but you shouldn't be too greedy. Yes.
I just want to point out there's a very elementary reason why the bounds always shrink as you crank up the dimension, which is just that the Gegenbauer polynomials in a given dimension can always be written as a positive sum of the Gegenbauer polynomials in lesser dimension.
Correct.
Or in other words, a consistent theory in high dimension is always going to be consistent in lower dimension.
Correct. Okay, so I'm gonna flash this. Maybe this is something can be discussed in later days, but by looking at scattering of 4 photons, two scattering of photons in the presence of gravity. So here is Einstein, Hilbert, Maxwell plus the leading higher derivative corrections. You can derive certain bounds on these coefficients. In fact, in the absence of gravity, you quickly prove that alpha 1 and alpha 2 have to be positive. In the presence of gravity, alpha 1 and alpha 2 are allowed to be a little bit negative, and the physical intuition for that is that gravity gives you a Shapiro time delay, which compensates for a little bit of time advance. So the causality relation that come from having alpha 1 and alpha 2 positive are sort of compensated by gravity. And this is unfortunately bad news for attempts to prove a version of the weak gravity conjecture, which they call weak gravity conjecture, from these methods, because that conjecture would be true if alpha 1 and alpha 2 were positive, or in terms of this G2 and F2, if you were inside this darker blue wedge, but gravity allows you a little bit of a wiggle room. Now, of course, this does not mean that the black hole weak gravity conjecture is wrong. It just means that these methods are not useful. So let me leave it at that.
How
Yes.
large is this wiggle room?
Sorry?
How large?
Okay, so here,
is it bounded?
these authors should, maybe you can tell us how hard it is to do this in dimension greater than 4. These authors did this in 4 dimensions, which violates my original statement that in 4 dimensions the story is ill-defined. And so if you actually read the slide, you see here there is an infrared cutoff. They had to introduce an infrared cutoff to make sense of the story. And so you see these, you can read the width here is m squared over m Planck squared, but there is an additional log that comes from the AR cutoff. We can debate whether this is a reasonable thing to do, but anyway, I wanted to show this kind of work that has been done. Okay, so let me pivot to this other research program, which is in some sense even better defined, because now we're restricting from the get-go to meromorphic asymmetries. So the analytic structure is completely well defined, and here zeros are Shapiro, and which, as many people have said, it looks truly miraculous from a space-time perspective. In fact, the fact that you can now look at arbitrary 2-2 scattering of massive states, and it all should hang together in a consistent structure is truly remarkable, and so that prompts the question of whether string theory is the only framework to derive infinite set of meromorphic amplitudes of this kind. And here I am going to still assume that the Regge behavior is strictly better than 2. This does not immediately follow from what I told you earlier, because in what I told you earlier, it was important that we were looking at the full quantum, working at the full quantum level with a mass Planck that was large but not strictly infinite. Although I do believe, and we conjecture in our recent paper, that if you take carefully the limit of the non-perturbative bound, keeping the higher spin scale fixed, it will actually follow that J has to be strictly smaller than 2.
Does this amplitude obey that rigid behavior?
Yes, it does it because of the famous fact that the graviton regizes. So the S squared, so the graviton exchange has behavior S squared, and the higher spin exchange have higher and higher powers, but of course they miraculously sum into S squared plus alpha prime u. U is negative, and so you get that the leading Regge trajectory controls the Regge behavior, and it's consistent with J smaller than 2. Another way of saying this is if I don't assume that J is strictly smaller than J is equal to 2, then gravity alone, without any higher spin extension, is consistent. Which, of course, you could say, well, of course, 3-level gravity is consistent. But here we're looking at higher spin extension of gravity, and the moment you have higher spin particles, in order for the problem to make sense, you need to assume that the graviton really is part of a trajectory. You could have a situation where you have a Regge trajectory that does not go all the way down to the graviton. The graviton is an isolated state that does not regize. But that means that then gravity is completely decoupled from the rest, and there's no way to put it all together. So I'm happy to discuss this more if people are interested. But so let's now consider the further simplifying assumption that we have maximal supersymmetry where in 10 dimensions. So we want to find the higher spin extensions of type 2A or type 2B supergravity. And I think any reasonable string theorist would think that the only possibility must be type 2A string theory or type 2B string theory. What else could there be? So this is a target. So if this is sort of a benchmark for our methods. Can we establish this reasonable conjecture by completely abstract arguments? And it turns out here there is this gigantic simplification that I don't have to deal with the polarization of the graviton. The 4-point of the graviton is captured by an effective scalar amplitude of 4 massless scalars who drastically improve Regge behavior. So the Regge behavior is now better than -2. And that the amplitude at low energy behaves like this. So 1 over STU is the graviton pole, and then the other terms are analytic. And in fact, of course, you could go ahead and compute G0 in string theory. And G0 is related to the R⁴ correction to Einstein gravity. So the fact that you jump from 1 over STU to G0 tells you that R² and R³ are forbidden, which is a consequence of the world identities. Okay, so here is what we did. So we imposed these completely general conditions, and as promised, we can derive bounds on homogeneous ratios in units of the cutoff. And here's how they look in the space of the first two, G0 and G2. And so we find that this region is allowed and whatever is outside is excluded. And we're also able to find an amplitude that explains this red line up to this dot. And it's a stupid amplitude of this form. The reason that this amplitude is stupid is that you see there's an infinite power of states with arbitrary high spin at s equal m squared. If you expand also in T and U, you will find they have arbitrary. And this is a violation of locality. So we have now imposed the fact that there should be no accumulation points or no infinite power of states at isolated points so far in our assumptions. And so, well, this is a possibility, and we get it at the border of at the boundary of the allowed space, where we want to remove it. And so to remove this unwanted story, and so also you can also see that string theory lives safely within the allowed region. You may wonder why string theory is not a point, but it's a whole Fed region. And that has to do with the fact, the somewhat trivial fact that for fixed cutoff M, I can vary alpha prime. And if I do that, I get a whole space of amplitudes, and moreover, convex linear combination of amplitudes are still allowed, which means that the convex hull of string theory without arbitrary value of alpha prime, one of alpha prime bigger than the cutoff, gives me this whole region. But actual string theory, where we take the first massive string state exactly at the cutoff, is to say it differently. Fix the string scale. The cutoff could be smaller than it, but that's a stupid thing to do. I should push the cutoff all the way up to the string scale, and then I will be sitting at that point. Anyway, so then
Is this cutoff in the dispersion interval?
it's the cutoff is essentially, yes, it's a cutoff that we're assuming in the derivation of the dispersion relation, we are integrating from a certain m square on. What I'm
confused about is if you're working with gravity, you have to take into account black hole creation. So what do you do about that?
No. First of all, this is just tree level. So
No. But you're saying you're trying to learn about the amplitude. So large enough S and fixed U.
But what would you say? What is the problem in the Virasoro-Shapiro amplitude? There's no problem. It's a meromorphic amplitude all the way. Of course, in full-fledged non-perturbative.
I believe Virasoro-Shapiro at very high S anyway, because for that reason.
That's exactly right. So what we're doing here, we're assuming that there is a perturbative expansion, and we're interested in the leading tree-level term, the analog of tree-level string theory.
Okay.
Yeah. So we're trying to look at the space.
You started the talk with these axioms about the general S matrix.
Right, and then absolutely, and I had a whole part to talk about that, and now I'm looking at this smaller, somewhat more comfortable corner of the problem, where I assume that I have a perturbative expansion and the tree-level approximation is reasonable, and I look at the tree-level approximation. But of course, this is not a fantasy; it's exactly what happens in string theory. So we want to put a bound on the possibility for meromorphic extensions of.
Can we also say that in the regime where you would get a black hole, then that would the 2-to-2 graviton would be exponentially suppressed?
Absolutely,
And
yes.
so then that's consistent with your assumptions, right?
Well, of course, there's no contradiction. I'm just saying I want to look at this space of meromorphic amplitude. If I were to do this in the context of large NQCD, to give another example, again, I would be looking at the leading one correction. Well, extreme large N is just everything factorizes, but the leading 1 over n squared correction would again be of this kind, a meromorphic amplitude with isolated poles. Anyway, so we insist that we only have finitely many states at some scale little m, and then with a finite gap to the next state. And in fact, we find, rather remarkably from our procedure, that we couldn't put an arbitrary spin or even an arbitrary combination of spins. The only possibility is a scalar, but remember, this is a scalar in this auxiliary amplitude, and so by the time you repristinate, you restore the polarization dependencies, it really means that this is a whole supermultiplet with spin 4. And if we do that, we find another exclusion plot where we're now putting a bound on the on-shell coupling on this exchange scalar in terms of the cutoff. And here something truly miraculous happens. We see that there is a sharp decrease, a plateau and a sharp decrease at a certain value of the mass of this gadget, which is precisely the ratio that we find for the first 2 massive levels in string theory. So by assuming almost nothing, we find the correct slope of the string theory edge trajectory. Notice, however, that the on-shell coupling is strictly bigger. And the question is, if I go back to the previous plot, I had not, I emphasized the red line, but not the blue square. It turns out that the amplitude that lives here is the same as the amplitude that lives here. We can analyze it numerically because by the solutions which lie at a point of the exclusion boundary have a unique extremal spectrum, which you can analyze numerically. And we find, rather beautifully, a linear edge trajectory. So this is a very curious solution of the Bootstrap problem, which appears to contain a single linear edge trajectory. It's a little unclear what it means because there are no-go theorems that say that there shouldn't be solutions with a single edge trajectory, but perhaps it's a bit exotic, or perhaps it's only approximate. But what I want to emphasize is that here again, by almost pure thought, we landed on the linear edge trajectory with the same slope as string theory, by imposing essentially nothing. And now you have to just impose a little bit more or look at a slightly more elaborate set of observables. For example, the obvious thing to do now is we found this intermediate state, now put it on the external leg. and look at the system of two amplitudes where both the gravity and the first massive state appear, that is supposed to be extremely constraining, and perhaps that will corner you on string theory as the only possible solution. Yes?
So what are the assumptions in the no-go theorem? What happens if you have this?
So, well, they had to use Regge theory, which is a bit of an art, and so there is some fine print there. They had to assume that there are no Regge cuts, etc. I mean, as we all know, no-go theorems are only good because they have interesting exceptions, and this may be one. So, okay, so I'm going a little bit slower than anticipated. But anyway, so this gives you, I will say nothing about the non-perturbative asymmetrics approach, which is valid in non-perturbative regime. Look at the papers by Guerrieri, Vieira. In fact, I recommend you look at the talk by Andrea Guerrieri, Strings in CERN, as a starting point. And now I will move on to a DSCFT. And we are interested in the regime where the Planck's mass is much bigger than the DSK, which further could mean that we are in the regime where Einstein gravity is reliable. Perhaps you could have an additional scale which is not negligible, as for example for higher spin states given by string massive states in ADS. And here, of course, there's a well-developed technology to study conformal correlators, including the numerical conformal bootstrap. But here, if you think about it for a second, the issue is that double trace or multi-trace operators from the abstract OP viewpoint, well, of course, they will appear in the OP of your two external states. But in this bulk description, there are multi-particle states. And instead, you want to focus on putting bounds on the effective field theory where the fields are the single trace states. So the naive OP technology is not going to work. So you need to develop a technology that throws out the multi-trace states in the OP and focuses on the single trace contribution to the OP. So if you get anything out of this part of the talk, it should be that dispersive some rules are designed to do that, to filter out the multi-particle contribution in the operator product expansion and to focus your attention to what you're really interested in, which is the single particle states. Okay, so this is something that really necessitates Lorentzian kinematics. And okay, this part of the talk is, I don't think I'm going to be able to do it justice, but again, at the level of caricature, perhaps I can do it. The relevant notion is this Lorentzian object, which is given by this double commutator in the following kinematic configuration. Okay, so you see 1 and 2 are time-like separated, so the commutator is meaningful, and so are 3 and 4. And this is the same kind of Lorentzian kinematics that appears, for example, in the bound on chaos. So this object is, by definition, what is called the double discontinuity of the correlator, where I've written here in terms of Z and Z bar, which are the conformal cross ratios. And the moral lesson is that the double discontinuity is the correct CFT analog of the imaginary part of the amplitude. The dispersion relation allows you to rewrite the full amplitude. Maybe you have to do subtraction, but anyway, you can write the full amplitude in terms of the imaginary part of the amplitude. That's the usual game of dispersion relations. The imaginary part that comes from the cut allows you to write the full analytic functions everywhere. That's what the dispersion relation does. In a similar spirit, the full correlator is reconstructed from the double discontinuity. So double discontinuity is a great invention because it's the analog of taking the imaginary part. And now you can see why you're going to be able to extract the single particle states, because by taking the imaginary part, you're precisely doing that. You're focusing on the intermediate exchange. And indeed, as it must be, the double discontinuity has a beautiful property of annihilating exactly the conformal blocks that correspond to the double trace contributions. So by taking the double discontinuity, you purify your state from the double traces. Of course, this is true to leading order in N. The double traces will get anomalous dimension corrections, which you can turn to your advantage. I use this technology to compute the 1/n square correction anomalous dimension by taking the double discontinuity. And this is by far the most. This is analogous in spiritually to these on-shell methods that people use to construct loop amplitudes by squaring tree-level amplitudes. It's the same idea. By taking the imaginary part, the amplitude factorizes. And so this is great invention during Caroniot and others that allows you to import these on-shell techniques to large N conformal filters. Okay, so maybe I should sort of skip this part, but the idea is that, let me be quick. So we start again from this kinematic configuration, but now 1 and 3 are space-like separated. So this is 0 by causality. So now we're going to process this 0 in some clever way. First, we integrate x1, x3 along space-like separated null rays by integrating over x1 plus and x3 plus with a certain kernel, whose significance will become meaningful in a minute. So we had 0, we still get 0 because just integrating. And then we use this FAT that you may or may not know. The null integrated operators kill the vacuum. So for free, I can replace the previous gadget, phi4, phi3, with a commutator because the other term does nothing. And so lo and behold, I'm getting an expression that 0 equal to certain sum of things which are written in terms of this double commutator, which is the d-disk. Now, that's almost true. And it would be true without the kernel. But because of the kernel, well, the kernel you need to control carefully the endpoints of the null integral. So lo and behold, when all does settle, you find a dispersive sum rule. We catch a few additional contributions from low twist, which are encoded in these kernels. As a technical point, which is perhaps more than a technical point, one needs to use an additional assumption or conformity, which is now have been fully shown from the axioms, which is validity of the light cone OP in the second sheet, but let me not dwell on that. Anyway, so basically now using these CFT sum rules, which are the end of the imaginary part, you can imitate step by step the procedure that led to the dispersion relations in flat space. And you separate your contribution to the 4-point function in a light and a heavy part. And the good news is that taking the double discontinuity suppresses double traces. And so lo and behold, you have a dispersion relation that relates the effective field theory coefficient at low energy to some heavy stuff, which is positive, which is complete analogy to the flat space sum rule. In fact, the analogy is so strict that if you have derived dispersive sum rules in flat space, there's a now well-developed technology to uplift them to ADS and translate the bounds that you had earlier in terms of bounds for your effective field theory coefficients in ADS. Okay, I realize that this part was a bit technical, but what can I do? So let me just mention a few, yes.
So if you take this in string theory, can you specifically identify what different contributions are? So
Yes, so that's my point 3. So the first application of this story is what I would consider as pretty much a proof of HPPA's conjecture that any large NCFT where the higher spin gap is holographic. And this just comes from looking at this 4-point function. For example, the simplest thing you can do is to look at the 4-point function with external scalars, but with exchanging a graviton or a stress tensor in the middle. And by uplifting the flat space bound that we had earlier to this ADS story, we find that the higher derivative terms in the ADS effective action are suppressed. And they're suppressed by what? By inverse powers of the higher spin dimension with precise coefficients. And that's HPPS. And of course, if you're really perverts, you want to do this for the 4-point of extension, which is a nightmare, but that surely doesn't deter our powerful colleagues. And they're doing that. So, and then, for example, if you take the d equal to 5 plots that I was showing earlier in flat space for this higher derivative correction to gravity and reinterpret them as certain bounds in ADS5 by this technology, then you get to do something very cool, because the higher derivative, you will recall that by Henningson and Skenderis, in Einstein gravity, the A and C anomaly coefficients are equal. But, well, the higher derivative corrections contribute differently to A and C, and now you get to do something very cool, which is to put a bound on the difference in terms of the higher spin scale with a number, 23. Another game you can play is focus on a very specific theorem you want to solve, which is 3 levels in theorem S5 times S5. Of course, here, well, there are various ways you could play the game, but the game was played by these authors was to input the non-spectral data from integrability. We know the spectrum of the first few line states is very precise for any value of the top coupling. We also have some other information about integrated correlators from localization. And by inputting this information into the dispersive sum rule, we get to compute the OP coefficients. So, for example, the OP coefficient that for two external 20 prime and the Konishi is very precisely nailed for every value of lambda by this technology. Okay, so let me emphasize this point again. In principle, the CFT story is better defined in terms of axiomatics. Can we derive all the desirable property of the S matrix Bootstrap from taking the limit? And I want to highlight these beautiful papers by Wout van Res and collaborators in recent years, where this is done, but not quite finished. And so these are very careful papers where you put rigorous estimates on starting from the OP density, you get estimates about what happens to the S matrix partial wave expansion, et cetera, and well, I think it would be very nice to make this a theorem.
But you couldn't see brains from this.
No. So again, we are working. So I'm assuming. Well, why couldn't you see brains?
Or how would you see them?
Well, so
How would you distinguish
okay, brains I haven't thought about. So here I'm in standard S5 times S5 story. The Planck scale has to do with n squared. Brain will have to do with n.
Yes.
So I would have to think about that. But here we're definitely assuming. Well, presumably they're outside the realm of this technology. But I would have to think a little bit more. Yes.
So, if when you want to do a DS safety, you put the boundary condition for the gravity for the DS.
Yeah.
And okay, as long as you're like large n, it's fine. But how do you know that that's like a good boundary condition near the flat space? If you want to go like real gravity, like 5 and 10, say. I mean, probably it is. I don't know, but for me, it's never been clear.
Well. I mean, you have to assume that there is a family of theories, right? So how does the flat space limit work? You have to assume that you have a family, a consistent family of conformal field theory with ever-increasing value of n, where the theory approaches flat space. I think that's part of the assumption that such a family exists.
In many cases, it doesn't. Like, I studied like 15 ADS, just normal and then in some cases you don't have these families. I mean, they don't get to flat space; they are truncated, and I don't know of like.
Well, but here, don't you want to invoke the fact that one thing we know about gravity is how it behaves at large distance. We may not know how we have a short distance, but asymptotically.
Oh yeah, this I agree with you. Yes,
so
absolutely.
So I would say that that's not the tricky part.
Okay, yeah.
If you're trying to think about confinement, in ADS for Yamil's theory, yes, of course, there is an issue what happens at low energy, but for gravity, it's, it seems very reasonable to think that asymptotically far away gravity is just gravity.
Okay, I agree. This makes sense.
So, okay, so now, so that's what I had to say, and now this is a much more tentative part of the story. I have very little to say about symmetries, but perhaps Daniel should wake up. So my desire here is I would like to play a game, and maybe you want to play a different game. It's okay, but the game I would like to play has the following rules. I would like, if possible, maybe I will give up on this game, but the game I would like to play, I like to phrase the question of symmetries in the context of quantum gravity, especially in the context of ADS quantum gravity, trying to use as much as possible just the kind of axioms for local operator correlators that I have emphasized here. Try to avoid algebraic quantum field theory. I have nothing against algebraic quantum field theory, but it's a little mysterious to me. And the relation between the standard axioms in terms of local operator correlation function, algebraic quantum theory, is very unclear, at least to me. But I don't think there's a precise logical connection. It's unclear whether one implies the other, when one implies whether subsets of the other, etc. So maybe eventually we will give up and realize that this game cannot be played.
Well, sorry, but I mean, I would at least say that the issue is the algebraic approach knows more because it knows the things where you need to use modularity.
Absolutely, the algebraic approach knows more, and so I like to tie my hands and try to be as conservative as possible. Just start from things which to me are completely uncontroversial, such as local operator parameters function, which converges when far away from other operators. This is something we can really see from the bulk description, right? I mean, we could derive, in some sense, the operator parameters function from the semi-classical theory in the bulk. So I would say this is a very uncontroversial property, whereas other properties of the algebraic framework, such as the splittability property that you emphasized in your paper with Hiroshi, are less clear to me from a bulk gravity perspective.
I mean, for example, I think generalized free fields obey
Yeah,
the Whiteman axioms, but
I'm coming to those.
yeah, they certainly have global symmetry.
I'm coming to those. So that's the game I like to play, and I think it's, even if we fail, the failure will be instructive. And so for example, the splittability property. Let me be provocative. Quantum gravity is mysterious. How do I know? It could be that there is an ADS quantum gravity theory which is in some sense consistent, but where the boundary theory does not obey splittability. Why not?
Does not obey what?
The splittability property, which is something which you can phrase in algebraic quantum field theory. But the operator parameters function, I think, is sacred. So I would say, in the spirit of trying to be as conservative as possible, let's try to play this game and see how far we can get. So okay, let's discuss this a little bit more. So obviously, if we want to have any hope of addressing the issue of absence of global symmetry in quantum gravity, we need to impose some locality condition. And the most straightforward way of imposing the locality condition in RD is, again, convergent parameters function and very much existence of a locus energy tensor. These are things that this is defined in terms of a bunch of set of operators and OP coefficients. I go through the list, and whether the set center is there or not is something I can immediately detect. Yes?
So with those two assumptions, can we even prove that, for instance, if I have a conserved current, there must
Well,
be
I'm
some
coming to that. Well, that's the question, but that's going to be my next slide. And then, as Daniel was emphasizing, well, maybe this is not enough. Maybe we need to say something about non-trivial topologies, for example, modularity, or, which is much the same, something about the presence of defects and boundaries. Okay, so that's the game that I would like to play, and let's try to ask, which I think what Miguel was asking, whether we use in this axiomatic framework, tying our hands, as I said, we can prove abstract Noether theorem. So first of all, let's perhaps this is already obvious to everybody, but let me remind you the motivation for this in the context of this workshop. So what we're trying to establish is that global symmetry in a local CFT is something that corresponds to a gauge symmetry in ADS. And here I put gauge symmetry in quote because I'm one of those people that really would like an alternative history where the word the phrase gauge symmetry had never been used. As we all know, gauge symmetries are not symmetry, are redundant in the description. This is a mantra that we have heard a million times. But okay, I think we know what we mean. In particular, what we mean is that given that we are assuming that there's a semi-classical regime, if the theory of the bulk is fully quantum, then, well, we don't know what to say. But we're assuming there is a semi-classical regime where then we can identify for example, if we have a continuous symmetry, then there should be a bulk gauge field with Dirichlet boundary condition, which is dual to the boundary curve. And again, we can nitpick and be very precise about this, but I think it's clear what we mean. And again,
if you said asymptotic symmetry, then you wouldn't have to put this.
If I said asymptotic symmetry, I wouldn't have to put this disclaimer. I would be reluctant to use the phrase asymptotic gauge symmetry because that confuses the story. But I think we understand. We all know what we mean. Of course, the fact that the symmetry is gauge means that we are mostly modding out by it, except that a little bit of it is left to act non-trivially on the boundary, and those are the gauge, quote-unquote, gauge charges that correspond to the global symmetry in the boundary. So we can be infinitely pedantic about this, but I think we're on the same page and we know what we mean.
Maybe just make one comment in this direction. I think another thing that can be said, I don't object to what Daniel said, but another thing that can be said is that it corresponds to an emergent one-form symmetry in the bulk. And this can sometimes be important because, for example, where if we had a non-invertible continuous symmetry, for example, that would correspond to a non-invertible electric one-form symmetry of a bulk, which could be described as a gauge theory, but maybe you don't want to do that.
So,
sorry?
There are no one-form
Emergent, approximate in the infrared.
But it's an exact statement in the boundary theory, so why should it be approximate in the bulk?
Because that's what corresponds to.
No,
so
long-range gauge symmetry is what corresponds.
So yes, so Hiroshi and Daniel have this definition of a long-range gauge symmetry. It's as good a terminology as any other. I prefer if we could have a terminology where the word gauge is completely excised, but it's okay. So
Sorry.
anyway, so let me phrase the question, then we can debate it. So again, this audit is very sophisticated. You're all categorical. You want to do non-invertible. You want to do all sorts of things. But let's stick with the most vanilla, most straightforward, zero form, invertible, compact, global, internal. Okay. For example, a compact U1 symmetry of the standard kind. And, well, it's clear how we would define abstracting the CFT. So we have a topological codimension different that combines with a stress tensor and sends local operator. That's something we clearly must require. And then if the symmetry is continuous, we should have a conserved current. And this is a notorious challenge. Prove this abstract version of Nether theorem from what? From some assumptions. And are the assumptions that I stated already enough? Or more is needed? That is the question. So, to the best of my knowledge, but you can tell me that you have a counterexample. I'm not aware of any healthy conformal field theory, and it's important. It's a theory, first of all. So I will not admit any sort of non-UV complete garbage. Has to be a theory. Has to be conformal. It has to have a discrete spectrum. Has to be unitary. It doesn't have to split trivially into two theories, so there has to be a unique stress tensor. So those are all requirements that I want. Are those enough in the axiomatic framework that I just mentioned with the standard axioms in RD to prove abstract theory, or is more needed? And in particular, what could be needed is something about information about our topologies.
What do you want to prove exactly?
I want to give you a conformal field theory, which is healthy in the sense I specified, and obeys the standard axioms of convergent, OP, etc. And it has a continuous global symmetry, continuous internal global symmetry, which is invertible, compact, blah, blah. and I want to prove that that implies the existence of a conserved current, meaning spin one local operator, etc.
Discrete spectrum means discrete on any spatial manifold, or like say just is on the sphere?
So at this stage, so this is part of the question. It's part of the question. So the most basic assumption, of course, is just the standard local operator spectrum, which is the spectrum of states on the sphere, and it's discrete in the sense there are, for any value of the dimension, there is a finite number of states of dimension smaller than dimension, so no accumulation points, finite number of states for any dimension, etc.
So I think Maxwell theory in 3+1 with gauge group R
In
times in 3+1 dimensions with gauge group R times R, I think satisfies everything on your list and is a counterexample.
No, because it has two substances.
You need I can probably fix that. I can add an F. Okay.
So it probably doesn't have discrete spectrum on any manifold.
Yeah, there's some manifolds where it doesn't.
But anyway, that example which I had in your paper, I can exclude with the demanding theory does not factorize trivially into two separate theories.
Yeah.
Now maybe you can come up. Okay. You see, I've been careful in phrasing this. In the first version of the slides I had last night, I said I'm not aware, and then I rephrased it as a question for the audience: Is anybody aware of a counterexample? I couldn't come up with one, but maybe there are counterexamples.
There are almost examples with the ABJ anomaly.
Right, those examples I would say they're not even theories because they're not UV complete.
Because the UV is because the Landau pole. So the Landau pole is how you want to. Yeah.
So in the statement of the question, how do we abstractly assume there's a continuous U1 global symmetry? Do we assume there's a conserved charge, or? So
I phrased it in terms of this topological group, which I thought that would be friendly to this audience. But there's a more pedestrian way to say it. So we have. By assumption, I have the CFT defined abstractly, so I have the set of local operators, and I organize them in representations of the symmetry. Given that I assume that the symmetry is U1 compact symmetry, it simply means that the charge is an integer. So I split the space of states in sets of integer charge, and then, correlation function based selection rules for that charge, and that's essentially all that is being assumed. So
you're assuming the ward identities as if they were current.
I'm assuming the ward identities as if they were a current, and then the question is there a current? I think either succeeding or failing in an interesting way in this direction would be important because this is the zeroth order question in trying to rephrase the question about symmetries in this abstract language. And of course, we have tried. And the obvious thing to do, you take a 4-point function of charge operators and try to argue that, for example, you could take phi star, phi star. In the phi star channel, you impose the presence of a stress tensor. In the phi star channel, there is no stress tensor, there's no identity. And then you want to prove that the phi star channel also must have the conformal block for the conserved current. I don't think this works. I think you're not going to be able to prove it this way. At least I couldn't. But of course, this is just this absolutely most stupid thing you can try. We have infinitely many correlation functions to play with. We can do large charge. We can do all sorts of games. Are these assumptions enough? Or can somebody come? Well, the fact that we couldn't easily come up with a counterexample is perhaps indication that they're enough. And so this is what people were saying. Of course, it's easy to find counterexamples if we relax locality. And one particularly nice example is the non-local ON model, which is a true, legitimate, good theory, for example, in 3 dimensions. But this tree does not have a local stress tensor, so it clearly evades one of our assumptions. Generalized free field theory, of course, is another example. I simply take a complex field of arbitrary dimension greater than 1 in 4 dimensions. This has a U1 symmetry. It also doesn't have a stress tensor, but you could say, well, it's a generalized free field. But there are generally interacting theories which can be obtained, for example, by standardized free field theory and doing some RG that are also counterexample, well, they obeyed the fundamental assumption they had about locality, which is the existence of a local self-tensor. Maybe more is needed. For example, I think there is a plausible sketch. So I was going to discuss more in the black, but I think my time is up. There's a plausible sketch of an argument in 2 dimensions using modularity. And the idea is that if you have modularity, then if you take your topological operator and you switch your head on the torus, that introduces twisted sectors. But a twisted sector on the cylinder in a conformal field theory can be mapped to a local operator on R2. And if I have 2 local operators of opposite charge, that basically defines a way for the local, for the topological line to end.
Is your group continuous? Or finite?
At this stage, the group was continuous, because I want to prove the existence of a current. So using that kind of sketch, and if you are able to carefully control the UV properties at the endpoints, you could try to define the current. This argument is too formal for my taste, but it indicates that perhaps the way to go is to, for example, do something like the thermal conformal bootstrap, which is consistent taking the theory on a non-trivial manifold. For example, you need the circle, and maybe there you will be able to prove the existence of this current. Or not, or perhaps the RD is sufficient. But I think understanding this in this language, which again is the game I want to play, purely within the standard OP axioms of conformal field theory, whether or not one can prove abstract negative theory. And then, of course, once you have that, then we can start thinking about global symmetries, which are global in this sense, and those should really be forbidden. But it's not clear why they're forbidden, because in this context, if you could prove abstract negative theory in this language, at least for continuous symmetry, you would have a version of the statement that a DSFT, the DS quantum gravity theory for continuous vanilla symmetries, they have to be gauged in the standard sense. Anyway, that's really what I had to say. I don't really have anything intelligent to say about approximate symmetries, and that's the end.